Okay, now let's do this question. Okay, have a read the question, pause the video if you need to. In this question, we need to explain the difference, basically what is the Faraday's law and the Lenz's law. Okay. Now, step 1, go to your cheat sheet, have a look at mine. Okay. Now, copy Faraday's law and the Lenz's law down. Okay. So the idea is Faraday's law, copy it down from the cheat sheet, all this word copied down. Then, okay, then what you need to do is, this is compare and contrast. So the Faraday's law, after you copy down all the word, now just say that Faraday's law is basically the EMF is proportional to the change of magnetic flux on change of time. However, Lenz's law determines the direction of the current. The EMF is proportional to the inverse this. Okay. So Lenz's law, okay, ended that minus sign. Okay. Now let's go to the next question. Now, in this question we have a solenoid. So what's happened is we need to indicate the direction of the current. Okay, now we have a magnet and the magnet is moving towards this thing. Okay. Then we need to find the direction of current, the induced current. So remember, system doesn't have change. Okay. Look at the wire without this magnet. Okay. Without the magnet, the wire does not have a magnetic field inside. There was nothing. Okay. Suddenly, a magnet comes through, okay. And the magnet creates a magnetic field in this direction. So the wires are not happy. What does the wires want to do? The wires wants to generate a magnetic field in the opposite direction to cancel this out. Okay, so use your right hand rule with what does the wires wants to do. Okay. Use the right hand grab rule, put your thumb to the right. Okay. Now we figure out that. Okay. Now, sorry, not to the right. Okay. Now, just remember inside. Okay. Now, inside the solenoid, okay, the magnetic field has to go to right. Okay. Now, have a look at those outside wires. Okay. So behind those wires, the magnetic field has to go to the go to the right. Okay. Now use your right hand rule. Try to make your finger. Try to grab one of those outside wires. Okay. So make the magnetic field goes to the right inside. Okay, inside those solenoid. So if you grab it, you find out the current actually goes downwards. Okay? If you grab it like this, the current goes down. That's the only way it happens with outside wires. Okay? So what we can say is now the current for the outside surface layer of the solenoid, the current induced must be downwards. Thus, if you follow the wires, current travels from left to the right through the resistors. So is left to the right. Next question. Okay, now in this case, we have a magnetic field like this, and someone is pushing this loop of wire from the left to the right. Okay, now we need to find, it's a multiple choice question, we need to find which one of the following, actually is the voltage, the EMF, and the time graph. But let me, what I'm going to do is, let me go through this process in detail. Now, remember Faraday and Lenz's law. So initially, at this position here, there's no magnetic field inside the loop. The wire is happy. The wires are happy about this. So once it goes in during the process, it goes in to the magnetic field. The wire is not happy anymore because there is a magnetic field going to go into the page inside that wire. So during this process, the wire what the wire tries to do is, the wire tries to create a magnetic field which is out of page to cancel the incoming magnetic field. So he feels like that there's no magnetic field inside him, inside the loop. Okay, so use our right hand rule. Okay, now if the magnetic field has to come out of the page, okay, try to grab each side of the wire, you're going to figure out that there must be the direction of the current. The direction of the current must be this. Okay? Use the right hand grab rule, so the direction of current must be anti-clockwise. So there's a current come out of the page. Okay, done. Now, once the loop went into the magnetic field and travels inwards, okay, there's no change of magnetic flux anymore because the magnetic flux in this area is constant. Thus, Faraday told me there's going to be no current generated, no induced current, no induced EMF. Okay? So this will be no current. Okay? Since the current or voltage produced only when there's a change in magnetic flux. Okay? While the loop travels into the magnet, there's no change of magnetic flux, thus no current. However, when it comes out, the story goes on. So, according to Lenz, Lenz's law, so what's happening is, while the loop in the magnetic field, he's happy. Okay, he get used to have a magnetic field inside him into the page. Once he leave during the process that leaving the magnetic field, he's not happy. He wants to have a magnetic field inside into the page. So what he tries to do now is he tries to create his own magnetic field. That's what the wire wants to do. I don't know why they appear like that, but they just do. Okay? Once they get used to have a magnetic field inside, they want it once they get out. So, so during the process, it coming out, the wire tries to create its own magnetic field, which is into the page. So use our right hand rule again. Okay, inside the loop, the wire has to be into the page. Then use your right hand rule. Try to grab each wire. You find out we should have a current flowing clockwise. So note that. Okay, Now, note that before we have the voltage, we have the current in one direction. In the middle, there's no current. Then afterwards, we have the current into in an opposite direction. So look at those following graph. A is wrong because the current is in the same position. They are positive. Lenz told me the currents are in opposite direction. Okay. Now B, no, B is wrong. Okay. Since inside the magnet there's no current, there's no induced electricity. Okay. C could be right. I have I have induced current in one direction, and in the middle is 0, then I have induced current in the other direction. That could be right, but D is definitely wrong, E is wrong. Also F could be right, but now the key point here is the loop moves at constant speed, 2 centimeters per second. Okay, so the speed is the same. Okay, remember the voltage is basically the change of magnetic flux over time. So the change of magnetic flux over time is the same, because the speed is the same. Thus, the voltage generated must be constant. However, in F, the voltage generated is different, means the rate of change is different. So C is going to be your final answer. Now look at this question. So in this question, now we need to find, it's the same question. Okay. Now what we need to find is, we need to find the average EMF induced. So in this case, use the equation. EMF is minus and the change of magnetic field over time, okay, which is N is the number of wires. We don't have it. No. So, so N is 1, okay, and the magnetic flux is basically the magnetic field times the area. Okay, so minus the magnetic field times area. But we have a speed. Now, for this question, it's really just easier to use another formula, which I didn't introduce. So, let me introduce you now. Okay. The magnetic flux, can also be calculated. Now we can use another equation. Now write this equation in your summary sheet. The induced EMF is basically can also be calculated. Can be also calculated by. Let me write it down there. Can be also calculated by velocity times the magnetic field in Tesla times the length. The length opposite, the length of the other direction, perpendicular to the velocity. Okay. Now, in this case, it's just easier to use this equation. Okay, so we put it in. So we have 2 centimeters per second. That's 0.02 meters per second, which is the velocity times the magnetic field, then times the length. Okay, so if now if it moves like this, okay, then the length they're talking about will be this length there. So which is 2 centimeters, 0.02 meters. Typed in your calculator, then you have the voltage of the wire. Now let's go to the next question. Same scenario, but this time now they want me to find, okay, yeah, it's according to the previous question. Now they want me to find the direction of the current, okay, through the ammeter, okay, whether from P to Q or from Q to P through the ammeter here. Okay, so now let's use our right-hand rule and Lenz's law. Well, we did that before. Let's do it again. Before, in position 1, there's in the loop there are magnetic field into the page. At position 2, there's not. So the loop of wire is not happy. He's going to generate his own magnetic field into the page, because they used to have it into the page, now it's gone. Then what he tries to do, use our right-hand rule. Magnetic field go into the page and try to grab each wire. Okay. So you get this. Okay. You get wire flow from this to point P, travel through ammeter, then go to point Q. But the question asks me, well, when they ask questions, they ask whether the current travel from P through the ammeter to Q, or from Q through the ammeter to P. So it's from P to Q. Yeah, that's the way they ask questions. The current has to travel through the ammeter or resistance. So it's P to Q. Okay. Now have a look at this again. Okay. Now again, same question. Okay, we have wires. We have wires rotate around a rope, and we have a magnet coming in, and basically the magnet coming in and comes out through, yep, the magnet that goes in and goes out. Okay, and they need me to find, yep, they need me to find current, the direction of current. Okay, the graph. Okay, now as we talked before, okay, as the magnet goes in, okay, there's a change of magnetic flux, thus there is a current or voltage. Okay? But once the magnet is already in the wire, okay, the wire does not feel a change in magnetic flux. Thus, the current will be zero. There's no change in magnetic flux over time, so it's zero. Only until when the magnet leaves, okay, there's no the magnetic field is weakened. When the magnetic field weakens, it's a change in magnetic flux over time. Thus, current is produced in an opposite direction as previous one. So what we can say is, okay, question B must be wrong because current has the same direction. C must be wrong because in the middle part, okay, the current should be zero. There's no change in magnetic flux. So A must be right. Okay? One direction goes to zero and opposite direction.